thank you very much for allowing me to talk and giving me this opportunity to meet you. I'm going to talk a little bit about some work I've been doing using accelerators. I've been at several different institutions while this has been happening. So I was in the University of Michigan before, and I was in Kaust in Saudi Arabia, and now I'm in Estonia. And all of these places have been very helpful in this, so I'd like to acknowledge their support. So just to give you an outline, motivation, introduction to supercomputing, accelerators, then a little bit about communication, an example application, and then example scientific application, and then some reasons to consider desktop supercomputing. So by that I mean you want to have a powerful cluster, but you make it your own as opposed to publicly available resource. Okay, so my main motivation is solve scientific problems quickly and at low government cost. Usually I don't provide the hardware, but I have to justify using it, and it's a lot of time quite expensive. So typical applications that people have for supercomputing, weather and climate prediction. So you want to be able to compute these things fast and accurately, and accelerators are very useful for this. Accelerators are also quite useful for visualizing the results. Another area which is of interest is computational fluid dynamics. So you want to optimize the design of cars, ships, even expensive cars like this. A substantial amount of computing time is spent designing these. So you want to make sure that the airflow around it minimizes the drag and you have high fuel efficiency, or in this case you're able to go very fast. Now the area of computational fluid dynamics, you want to be able to design jets. So you want to understand how they produce shock waves, whether there's going to be sound wave that travels to the earth and makes it uncomfortable for you. And again, you want to be able to do this fairly quickly because it's cheaper to do this on a computer than it is to run this in real life and have people complaining that the noise is unbearable. Okay, and another area is trains. So I had to come from Tartu. If we had a fast train, I could have been here in 50 minutes. And you want to design the train so that it moves quickly and doesn't consume too much energy because that's expensive. Another area, computational solid mechanics, computational material science. So this is related to some of the work I've done in my PhD thesis. And what you want to do there is optimize the microstructure. So there are special swords in Japan where they heat the material in such a way that you have these dendritic structures. And so the metal bends very well. It doesn't just break or fracture. But it's also tough, right? So the edge of the blade is hard. So if you have a sword, you can cut people up, which is the reason they did this. And then afterwards, once they figured out what was happening, they can make parts and knives and other things using this process. And if you can simulate it, you can figure out exactly how long to heat the iron, right? So iron processing is expensive. You can make it stronger or less brittle. You can use it more widely. And then another area is fusion. So if you can't design your train well enough so that it's cheap to move it, you create lots of energy using this, and then you don't care that the wind resistance is high. But to do this, you need to be able to control it and understand what's going on. So this is kind of a torus. They're trying to build a fusion reactor in south of France. And they're trying to do lots of simulations to make sure that they can control this. It doesn't become a nuclear bomb. Okay, so other areas, data analysis, machine learning. Those I know less about, and also it's much harder to get pretty pictures for those. So I'll just mention it. I know some of you are experts in this area. Okay, so accelerated supercomputing. This is the #2 machine in the world at the moment. It's Titan, has NVIDIA GPUs, K20X. So came on a little bit before November 2012. Hence the slightly older GPUs, but still quite powerful. And it's also expensive to replace this many GPUs at once. Okay. The current number 1 machine is in China. This uses Xeon 5. Again, slightly older generation. So a lot of times for these computers, they usually end up with things a little bit before they're released. So the supercomputers are kind of useful because you get people who are very good at programming and they can test out new technologies. And one of the things that a lot of the technology in terms of the Xeon chips and the Xeon 5s is from the US, but how they connect them up is actually all designed in China. So the networking is a huge part of these machines, because even though you have lots of high-powered graphics cards or Xeon 5s, they still need to be able to talk to each other. Okay, so let's just give you a brief overview of accelerators. So NVIDIA GPUs, this gives you about a teraflop of double precision performance. One of the things that's difficult is programming them. So Cuda is nice, especially for me coming from scientific computing, who prefers C and Fortran as opposed to OpenGL. But also supports OpenCL, and then OpenACC basically allows you to take your regular C and Fortran code and run it on the GPU. Right? So this is provided through PGI. They have a compiler that does this. They also have this Cuda Fortran. So when it initially came out, if you have a lot of old Fortran legacy code, you can run it on this with very minimal changes, and usually getting quite good performance. So the compiler is pretty smart in terms of getting it to run on the GPU. Okay. You have accelerators also from AMD. These are not quite as widely used. Again, they use OpenCL, and PGI also provides an OpenACC interface. They don't really support Cuda. So depending on what you're trying to do, you may actually have to use OpenCL if you want the code to work in both places. The optimizations required for the two are also slightly different, but it should run, which is usually the biggest obstacle. Intel Xeon 5. Again, also about a teraflop of double precision performance. This is, for scientific computing, the double precision is quite important. For graphics, it's not so important. So you'll find that for some GPUs, you get much higher performance with single precision compared to double. For the compute-related ones, it's usually about a factor of 2 difference. It accepts OpenCL as well, which is nice. So if you use OpenCL, you can use that everywhere. But the performance may not be quite as good. But it also accepts somewhat more regular interfaces, so OpenMP, Fortran, MPI, and then Silk, which is kind of Intel's, one of Intel's programming APIs. Primarily aimed at compute, but also does graphics. This is slightly different in that it doesn't have quite as many cores as the GPUs. So at the moment, these have 60 cores, and the kinds of applications you will look to run on this may be different than the ones you will look to run on GPUs. Price-wise, I think they're about the same for the top of the end, but Intel doesn't do too much in terms of low-end versions of these. Parallella is actually also a startup. They also use Kickstarter, and what they're doing is they have an ARM chip, and then they'll have their own accelerator kind of on the same board. Not quite as high performance, but the interesting thing is that for their best product, they can get 50 gigaflops per watt. Right? So if you're doing some kind of application where battery life is critical, then this looks like the future. You might want to have something like this. Supercomputing, this is also useful because the power bill actually becomes important. So if you're able to program something like this, then this may help you if you want to do further scientific applications, or if you want a mobile phone which you have to charge once a week as opposed to once a day. Uses OpenCL, C and P threads, somewhat targeted embedded applications. And I'll mention the Tegra K1. Again, also uses OpenCL. Slightly different model here is APU, and the idea here is you actually combine GPU and CPU within the same chip. So one of the things that people have complained about before is that they had to move data from CPU to GPU, or CPU to Xeon Phi accelerator, just depending on the nature of the task that was required. So CPUs are still very good for some kind of task where you need out-of-order execution or have a complicated workflow. Here they try and combine the two. Reasonably high single precision performance, not quite as good double, so it's a little worse than half. But a large number of programming APIs and maybe able, for some applications, to get more efficient results. Intel also has something similar. They call it HD graphics. They haven't really marketed it in terms of HPC, but same kind of thing. You have a CPU and GPU on the same chip. And for your low-end laptops, these are the kinds of things that are being used. So you don't have a discrete graphics card. You have one of these with both the graphics card and the CPU. The GPU, again, provides exceptional performance, so high floating point performance. You somehow want to be able to use all of these things, right? And if you notice, they all have OpenCL in common, but if you really want good performance on each of them, you still have to do a lot of refactoring of your code and retuning. So there's a lot of research to be done in terms of figuring out how to use these for applications. There's also a potential for surprises, so you kind of want to try them, and you may come across something where one of them does really well, or might do really well if you make a small change. Right? So the market, for example, for game consoles usually takes some of these kinds of chips and makes like modifications to them. So you'd like to be able to use this in supercomputing, right? I showed you pictures of Tianhe 2 and Titan, and those have lots and lots of GPUs. And one of the problems in doing scientific computing or other kind of parallel computing is that they need to talk to each other. And the technology for this tends to be quite expensive if they need to do it very well. So figuring out algorithms where they don't need to talk to each other too much, or they can talk to each other with delays, is of interest, and can actually also be done at a moderate scale. You don't need to use Titan. You can take 6 GPUs, find 3 undergraduate students, or 1 very productive graduate student, and after you really have a startup, because they've managed to come up with an algorithm that revolutionizes some area. Okay, so in terms of communication, you need to be able to connect these together. Cheapest option is gigabit Ethernet. This is what people use to connect computers together. You run the wires and you just get an Ethernet card. People have used this a lot. It's the cheapest option. So a card will cost you maybe 15 to 20 euro. And low bandwidth, fairly high latency. But if you have several old computers, you can string them together and actually do something useful with them. Next option is high-performance gigabit Ethernet. So here you get 10 to 40 gigabit per second speed, so it's a factor of 10 greater than what you had before. Price can also increase as a result. But there's a large community with knowledge of Ethernet networking, so the amount of extra things you have to learn to be able to implement this in a small cluster is not huge. So this looks like it'll grow. Currently, what a lot of people use for clustering is InfiniBand, so this gives you up to 50 gigabits per second. It's a commodity product, so you can buy it fairly easily. And before, it used to be a lot better than gigabit, 40 gigabit Ethernet. It's now maybe comparable. So it's unclear if this is going to disappear or if it will, the speeds of these, both of them keep improving.
Is there a particular manufacturer behind it, or is it a standard? Or?
I think it was Intel that made it.
So Intel is moving, so a lot of this stuff is moving on chip as well. So Intel actually just bought Cray's interconnect design team. InfiniBand, one of the largest providers is Mellanox. They have laboratories, I think, throughout the world, primarily based in Israel.
I was just wondering how actively it's being developed.
So
It
there
sounds
are-
like it's at risk of falling behind.
So they do want to release things that are maybe 100 gigabits per second. They have, I suppose, good interaction with manufacturers as well. But they are also looking at gigabit Ethernet and may end up supporting both. But yeah, it's not clear. In terms of price right now, I think they would be about the same for performance. The question is whether you have to learn a lot of new stuff. And both those communities do support research, so they're actually quite tied with universities because they can't do everything in-house. Then we have these proprietary interconnect. So this is what's used on the largest supercomputers in the world. So Cray has what's called Aries, and this was somewhat sold to Intel. Fujitsu has what they call Tofu. So figuring out how to connect up computers so they can talk to each other well is a bit of an art. If it's a small thing, you can connect everything to everything. Once it becomes large, you need to do something smart, both in terms of the hardware connections and in terms of the software. So if you have expertise in networking, this is kind of a interesting area to try out ideas. It may not be the most lucrative area because there's only so many supercomputers in the world that people are going to buy, but you can develop the technology there and then use it elsewhere. And IBM also has similar kind of interconnect technology. Right? So it's kind of useful to know this if you want to start programming these things. And a lot of the things you program on, say, the top 10 supercomputers now, you'll use for the next 10 or 20 years. Right? Everything just kind of filters down. So power of your mobile phone now is equivalent to the best supercomputer about 25 years ago. So interconnect, so for a high-end supercomputer, this is half the hardware cost. And you need to figure out whether you want to pay this. So if you're doing a custom application, so some applications will run for 2 years straight, and most supercomputers last 3 years. So if you can build something that works very well, at say a 6-node level, that's maybe a useful skill to scale up for some applications. Okay, so a lot of the work that I've done started off in mathematics, is for solving differential equations. I apologize if I bore some of you, but this may be a useful tool for introducing students to parallel computing as well. So this is a project to allow first-year students to be able to use biggest supercomputers in the world. One of the other problems with using these supercomputers is that it's very hard to verify the results of computations that people have had. People tend not to always publish their code. Sometimes it makes sense not to publish. You do a lot of very computer-specific optimization, so nobody's going to use it. But it's also helpful to have some basic idea what's happening or reference implementation, which may not run so fast, but if you need to do a verification run, it's there. So we use a fast Fourier transform and just briefly go over some ideas on differential equations. So usually use these to model how things change. So in this case, you can say you have a population, and this was used a long time ago, but the rate of the population growth is proportional to the size of the population. And you can kind of go through and solve this, and you find that the population depends exponentially on the time. Right? So 1900, early 1900s, Malthus said that if you kind of have this, then this is a bad thing because you get suddenly a huge number of people and there's not enough food to feed them. So this is a toy model for that. You can add other things to make it more complicated. so that at some point you get an equilibrium, right? The number of people balances the amount of resources that are available. Okay, so having introduced this, you can go on to doing something where you have spatial dependence. So now you might say that you're looking at how heat spreads, or how if you start off with a concentrated number of people at one point, they kind of diffuse, right? So this here is the function that you're interested in. It depends on time and also depends on space. And then you kind of do this trick where you assume that you can split into two parts, one which depends on space, another which depends on time. And then you end up with two equations which you can solve separately. And you kind of write out a general series solution using sums of these. Right? So some constant, an exponential decay in time, and then some sum of sines and cosines. So you can approximate functions using sines and cosines. So even though this is a specific function that doesn't look very general, by changing these constants, you can actually approximate anything in 1D that you will likely come across. Okay, so how do you find those constants? You suppose you have some initial function. So as I said, suppose you're living on a line and you have a lot of people concentrated in one place. Say they all happen to be living in Riga, and you want to find out how they will spread. So you can do this kind of dot product. So you kind of do a projection of this function and you figure out the coefficients. And then that allows you to write the function in terms of sines and cosines. And then once you have these constants using this formula, you have the full solution. Right? So it's an approximate model, but you can actually put in numbers here and it'll tell you how things are spread out in space and time. Okay. That was kind of nice. We didn't do anything in time. So you usually make a discrete approximation. And you can then approximate the time derivative, and you end up with some linear system of equations which you need to solve. So here you've kind of made an assumption instead of sines and cosines, complex exponential, and then this gives you a small system to solve for each one of these terms. Right? So this is nice. That means you can actually solve things. So one case we look at is the Schrödinger equation. So this kind of models a quantum particle. People also use modifications of this equation to model Bose-Einstein condensates. So these are interesting because they have properties which allow for magnetic levitation. If you have a superconducting magnet, you will put it in something very cold, which is likely to be made of this kind of material. So maglev trains, for example, may use something like this. It also allows for very efficient transmission of electrical energy. So the electrical resistance of these condensates is very low. So people are interested in trying to understand them, and therefore may want to simulate them. So we tried to solve this using Fourier transforms, and this is fairly easy to do on GPUs. We examined 3 different programming APIs. We did not super optimize the code, so we use NVIDIA libraries to do the Fourier transforms. And you can look at the difference in speed between what happens on a single CPU. This was an older CPU, so those have gotten slightly better. You see somewhat good improvement in the rate at which you can do the simulation. You also see that Xeon Phi is roughly comparable for these problem sizes. Right? The appropriate platform does actually depend sensitively on the size of the simulation that you're doing. So let's say at this point they're roughly comparable. The reason I say that is tuning can usually give you another factor of 2, and that can be critical. And even the manufacturers don't always know how to do this. Some of it is just trial and error. So if you get 1,000 people working on this piece of hardware, one of them is bound to get lucky and figure it out. Okay. Another area, just look at the 2D Navier-Stokes equation. You can do this in 3D as well, but we've run most of the tests on this. And the reason this is interesting is that, there's a lot of theory that people want to, or don't fully understand for turbulent flows. And some of that can only really right now be made sense in 2D. So it's nice to do large simulations of this. It's also of interest if you want to do weather forecasting. So if you want to do a global weather simulation, the depth is very small compared to the circumference. So it looks very much like a 2D simulation. So if you can do this well at a large scale, then you can also do weather prediction well at large scale. So you rewrite it slightly differently and then do the simulation. I'll skip this part and just show you a quick video. So this was done by if this comes up. Right. So this was done by Brandon, who was a bachelor student at the University of Michigan, and he's just looking at mixing of a vortex in 2D. Right. So this is something you could code up after a while and you do on a GPU. Right. The visualization here was done as a post-processing step. One of the interesting things to do would actually be to do this at the same time. And in particular, in the 3D case, it's very nice to be able to somehow immerse yourself. So being able to use GPUs to do 3D visualization and actually transmit this remotely is very useful. So stop there and move on to the next one. Okay. So you can use multiple GPUs. As I said, you wanted to simulate the weather of the whole world, and you can't do this on one GPU, at least not very well. So just before Titan came online, they put a small partition of Jaguar where they had NVIDIA GPUs on there. And there was another machine, Kingland, which also had NVIDIA GPUs. The GPUs on the two were exactly the same. The difference was how they were connected up. So Kingland used this InfiniBand interconnect, and Jaguar had Cray's older interconnect. Right? And both of them had about 1,000 GPUs. And over here what's shown are the different problem sizes. So you can go from 1,024 squared up until 32,000 squared, in the same kind of range of problem sizes. J here is for Jaguar, K is for Kingland. So Jaguar is a more expensive machine in this case. And you find, okay, for one GPU, they give you exactly the same time, because it's exactly the same graphics card. When you do more GPUs, Jaguar tends to do better at small problem size. And the interesting thing is that the largest sizes, they switch. Kingland does better. So Kingland is cheaper computer, but the way that InfiniBand works, it can actually take much larger sizes of data at the time. So when the problem size becomes large and you have to communicate a lot of data, the fact that it may take a long time to start up to go is outweighed by the fact that you can send lots of data at once. Whereas with the more expensive one, small messages go very quickly, but at the time it couldn't take very big messages. Right? Which is okay. I mean, for some simulations, you don't need to communicate lots of data. But for other applications, this may be useful. Okay. Ran some similar comparisons slightly later. This time Shaheen, which is an IBM Blue Gene machine, so this has no accelerators. Completely different architecture. So Shaheen's made to be very power efficient. So it uses lots and lots of cores, but they're not so fast. Similar to how GPU cores are not so fast, so that it can be energy efficient, which is how much it speeds up as you add a number of GPUs. Doesn't improve too well, but suddenly jumps. So the time in Titan was always much better for equivalent problem size than the time on Shaheen. But Shaheen, you kind of had this very nice decrease in computation time as you increase the number of cores you used. So both of these were, say, not too difficult to program. So we stayed away from Cuda. We used Cuda Fortran. We used OpenACC. So the changes going from a regular C or Fortran code to a GPU accelerated code are not too large. Of course, if you want to do visualization, you're going to need to use OpenGL or somehow mix Cuda with either OpenCL or something else. So the coding for visualization does actually become a little bit more complicated if you want to do it that. Okay. So to summarize, you've seen that the most expensive interconnect may not always be the most appropriate for your application. And it's helpful to be able to investigate this beforehand. And it's maybe nice to have a small cluster. Right? So some of the results I showed you there, you can actually do quite a large simulation on 10 GPUs. That's something you could have in your office, for example. So if you're doing CAD or you're doing some kind of design, then it's helpful to have prototypes of these. As I showed you, there was, I think, 7 or 8 different types of accelerators. Not all of them are going to be made into supercomputers, but for some applications, some might work a lot better than others. So these kind of student competitions may be a useful thing to do. So one of the things was pointed out here was computer vision, but there are other applications where this is useful, and your choice of accelerator may be critical, or it may suggest a feature change to the manufacturer. So it's nice to have these things and try and make use of them. So there's a link on some of the student cluster competition there, and conclude there with the fact that these are nice things to play with. NVIDIA is nice. I tend not to be too loyal, so I want to play with everybody just to see if some tool might be better than another one. Just to show you that this can be done at a large scale. So these were 3 students at Michigan, undergraduates. Mira is the, I think, number 4 or 5 biggest supercomputer in the world at the moment, and can use this to do a simulation up until 500,000 cores. Somehow you want to look at this. So again, a lot of these supercomputers are remote sites, so being able to stream this over and look at it in 3D or somehow make use of that, either on these regular computers or using accelerators would be a nice thing to add. And I've mostly focused on the scientific part, so if that's something that people are interested in, that would be of interest to collaborate on. And I'll show you, well, before I finish, maybe I'll show you some of the pictures that they have. So this is just his website. Just some of the activities. This is one thing he went on after doing the simulation. And the simulation, the Klein-Gordon equation. So they presented this at Supercomputing in 2012. Right? So 3D visualization, it's just a volume rendering, but they had to do this in post-processing afterwards. If you could do this in situ and make something that's immersive, that would be really cool. So, and if you could stream this as well, that would also be very nice. Yeah. Okay, so thank you very much for your attention.
Yeah, thank you. Questions?
Actually, I have one. It's not directly related, but I mean, I assume you have gotten the direct experience with the Xeon 5, right? Or,
Yes.
I mean, I was also introduced to it some time ago, and I was wondering. I mean, have you seen? Does it actually is it actually usable to run it as a replacement of a CPU? Because I mean, as far as I see, Intel is pushing out motherboards that will kind of support them for servers. I mean, I understand that the main target, of course, is parallel computing. But if you put such a CPU with that much cores in, let's say, I don't know, a general CPU, I mean, wouldn't the issues with the thread context switching we have now on like 4 cores would be solved? I mean, have you seen anybody try to just run a conventional OS on a computer with 60 Pi?
So we have a couple PHY cards. Intel says you can replace their OS with something else.
Mm-hmm.
I personally haven't tried that. It seems like it takes some getting used to. So the results I showed you for the Fourier transform, it took me a while to figure out problem sizes where I got about the expected performance that I would expect, given what GPUs support. For other applications, I think you're going to end up with that anyway, having chips with 60 or 100 cores. I don't think they will work for every application.
Of course.
But I think people are going to have to learn how to deal with that level of parallelism. So it's useful to experiment with it. I'm not sure what the performance of the next generation is going to be. So they're promising that it will be much more user-friendly. Intel compilers usually help you quite a bit. I would say almost, yeah. So at least for Intel CPUs, they seem to be as friendly as, say, the PChat compilers I found for NVIDIA. So personally for me, Cuda was a nightmare. I mean, it allows you to do very useful stuff, but if I'm doing scientific computation, I don't really want to write kernels if most of my code is loops. So if it can do loop parallelization for me automatically, I'm very happy. If I want to do something more complicated where I need lots of tasks and lots of scheduling, something closer to the Intel might be more helpful. So at least with the experiments that I've had, Intel is very good at doing lots of threads per core. So if you might have some kind of web applications where CPU usage is not very heavy, and you just need to run lots of threads, then this might be cost efficient. If you need to do graphics, and you need to do heavy graphics or more graphic-related stuff, I would probably go for NVIDIA. So they're each good, but it's unlikely that they will be very good for the same things.
So I mean, the baseline is because I mean I'm asking only because I've read about it in Wikipedia and I haven't like held the actual card in my hands. So it's not like a general purpose CPU, right? I mean, it has its own some kind of OS that boots it, and I mean use it like more like a peripheral device. You just cannot take motherboard and put Xeon Phi in as a main CPU and just run a I don't know a Linux or something.
So at the moment you can use it in 2 modes. You can actually SSH into it and run stuff on it directly. So you treat it like a little CPU. I have found that this is a very unfriendly mode to use because I usually have a code that I want to run on it, and it's a lot easier for me to write. So a lot of the files I use are on batch systems. So it's a lot easier for me to write a batch script that will utilize the CPU and then do what they call offloading. So it will automatically move the data onto the Xeon Phi. There'll be some parallelization directives, and it'll run. If code can fit within 6 gigabytes, then the offloading directives are very easy to apply. You apply one at the beginning. It's almost like an OpenMP directive, so it's like bang, directive, $, offload, and then begin, and then at the end there's a bang, directive, $, offload, end. So with those 2 lines of extra code, if you don't have huge memory consumption, it'll run on Xeon Phi. It won't run fast because you need to change for the structure compared to the CPU. But everything you do on the Phi will work well again on the Xeon chip.
Okay.
If you need very fine grain parallelism, the Phi is maybe not quite as good. Right? So if I want to do a long 1D FFT, so far I've found that I'm much better off on NVIDIA GPU as opposed to Xeon Phi. That being said, Intel have published a few papers saying they're doing very well with 1D FFTs, but I don't necessarily want to spend a year writing a very good 1D FFT code. I want to use a library. So it does depend on the task that you're looking at. Sometimes you may want to even use both, right? You may have an application where you move the data back and forth between the two. A lot of the ideas will be useful.
So any more questions about it? So from my side, probably this question, could you a little bit tell us more, what is it your everyday job duties in Tartu University? I don't know, what you're doing in the research projects now, or what?
So I'm still looking at these for spectral methods.
Okay.
I want to finish so I showed you a comparison between Xeon Phi and GPUs, but those were still single.
Okay.
And while I've done I've done a multiple GPU code, I would like to understand how well multiple Xeon Phi code would work.
Okay.
That's one project. Another project we're looking at is linear solvers. So a lot of these discretizations, Fourier methods are very nice, but they're not so great for engineering applications. And for engineering applications, you need all kinds of unstructured grids. You still want to run them fast and on GPUs. So we're looking at doing that.
And what kind of infrastructure Tartu University have for those research jobs?
Tartu has 4 cards for Xeon Phi on their current cluster.
Okay.
I have access to a cluster in the US. So a lot of so the thing with this supercomputing infrastructure is that it lasts only 3 years. So there's very few universities that can afford to buy a specific type of machine and use it entirely on their own. So usually what happens is you either use one of these European infrastructures or these grid infrastructures, and then you can actually try out your code in a bunch of different places, because usually doing very short test debug runs. So a lot of them you apply, you get an allocation, lasts usually up to a year or so, and then you need to renew. That's enough for testing, and so some of the big runs you can do. Yes, you can use a whole machine, but you use it for less than an hour. It doesn't make sense to ask a university to get a machine that size if you're going to use it for an hour an entire year.
Yeah.
But if you have 2 or 3 cards, you can buy those. You do a lot of your development locally, and then you apply to one of these places once you have your code working. And as I said, you can get a first-year student to do some of this. You obviously don't want them mining bitcoins because somebody's paying for this. But they can run a lot of simulations. They can do visualization. They can develop code. And it's a good way for them to be prepared to go out, because everything they learn, say, on these big systems now, will filter down. They're going to need to use this for the next 10 years of their careers. So I also do a bit of teaching, and yeah, trying to see if there'll be other people interested in maybe also having these competitions. So I know that the robotics is big, but also for the small clusters, there's a lot of other applications where it'd be useful to have these skills.
Are there any competitions here in Latvia for HPCs and that stuff?
Competitions?
Yep.
No, I'm not aware of any.
It's kind of undeveloped, some kind of part of market. I find. Yeah. Okay.
Actually, you mentioned a good idea. Which is the best of them to use for Bitcoin?
I don't know.
ASICs. And
I mean, yeah, that's well, that was my next question. I mean, is using GPUs better than ASICs or?
No, that's definitely not, because we covered those topics in cryptocurrency meetup, and I'm mining those Litecoins and other stuff on my home multi-GPU setup on a home computer. It's not it's consuming more energy than earning.
Well, it all depends on the algorithm too. So
At least you could warm up your room with this energy from cards and being rewarding by Bitcoin. You should pay for electricity at least. It's quite efficient electrical heater. So sorry. But it's still there's a couple of new cryptocurrencies like Ethereum, like not Litecoin, Dogecoin's probably not. Base, who's probably a little bit more convenient for GPU mining, but still there's a huge part of ASICs. And I think that the next cryptocurrencies will be more depending on CPUs, not GPUs, because they would like to be not dependent from ASIC producers and something like that. Yeah. Okay. Any more questions for Benson? Okay, Rudolf. Now it's your.
this actually was a really good introduction because I will be touching both Intel Iris and Cuda, so it was actually a really good intro. Before I actually go a bit deeper, I understood that I actually forgot to explain some of the fundamentals in the presentation, so I'll start with that. Yeah, and I'm doing a research project for my PhD. Where we are building a high resolution display wall. Well, the first intuitive thought would be that this can be based totally on hardware. I mean, you can get a cool server board with 5-6 PCI Express boards, but a card with 3 or 4 outputs in each slot, and I mean, well, you'll get like a system with many outputs. So why would you even have to do any research there? Well, if you have such a system, there are a couple of issues that appear. First is, as we've already concluded here, it's power consumption. I mean, to drive 4 or 5 high-end GPUs, first you need a really good power supply, you need cooling, you have a high bill. Then again, wiring. I mean, if you need some kind of display wall, which is located in an infrastructure like a train station, metro station, airport, where the actual processing would be located in some kind of data room and the walls would be laid out in the infrastructure, you would suffer from the wiring because all the digital cables suffer from the length limitations, which again, as you already mentioned, all the GPU approaches use either gigabit or something even better. So while the display walls suffer from the issues, people have been trying to improve this domain. There is a thing called Sage in USA, where what they did is basically, I don't know if you're aware, but there's a Unix windowing system called X, which basically allows you to forward the screen between computers, which is, I mean, it was intentionally made for people to be able to connect to servers and actually get some kind of visual interaction. But what they did modifications to the X windowing system and created an environment where you can like set up a big tiled wall. You would have some, let's say 4, 5, 6 computers driving the wall, and then you would have clients forwarding their content to like an X server, which would then lay out the contents on a screen. So this is kind of cool. I mean, you can have a great collaboration. You can have like 5, 6 people sitting in a room presenting their stuff and work on a big united surface. But the issue with this is that it's still limited to the resolution of source. I mean, if you have like an X-ray shot or a satellite map or something that is taken in a really high resolution, you basically still can't show it in full size if you have a computer which is, let's say, limited to full HD, right? So Sage is cool, but it still suffers from a lot of limitations. So when I first started my PhD work, I was really interested in this area, and well, I wanted to somehow provide the abstraction from the hardware. I mean, not to have you limited by the resolution of the monitor or output of the card or anything. Well, my first idea was I could write a GPU driver that would like simulate additional virtual outputs, and then I would just, I don't know, dump the data somewhere and send it over to network to the wall, and everything would run fine. But I mean, as you can understand, this thought just ran into the wall because, well, nobody's going to give you their driver sources, and you just can't just write a driver out of the air for, let's say, an NVIDIA rental card. It's, I mean, very work-consuming, and it would not portable. I mean, I couldn't run any OS on that. Well, I mean, you need any OS to run such a system because the things you want to stream to display wall, I mean, they can differ in all the possible ways. You may want to have just Windows with Google Maps, and you may have maybe Linux with some specified software which does some simulations. So you basically need to cover all the areas. And then, well, when I was desperate about the drivers, I started to think, I mean, well, people sometimes need to simulate video hardware, and how do they do that? And then I stumbled upon virtualization. I mean, GPU is actually one of the things that is very poorly virtualized. If you look at the virtualization systems we have KVM, VirtualBox, AS6, Hyper-V, and everything. I mean, they virtualize most of the stuff like hard drive, CPUs. You have direct access to the devices. But GPUs are somewhat left out of this sandbox, and most systems run their own simulated GPUs. Okay, there are some cooler systems like KVM which actually give you a direct through pass, and I'll talk about that. But the thing was that I saw that virtual machines is actually a great way to abstract from the hardware. I mean, you can have a system running which provides the content, and you can give it a virtualized graphics card which you can configure as you want. I mean, as per the needs of the wall. You want 6 monitors with Full HD? Okay, give the virtual card 6 monitors. You want 20 monitors? Give it. And that's in no way bound to the resources that are consumed by the underlying system. Because if you bound to a number of GPUs, let's say you present some content which runs all the GPUs at idle power. It's basically a waste of your money and the power, because you've bought GPUs that would have been denoted for, I mean, gaming and running Far Cry, and you're just streaming some browser data and the cards are all at idle. I mean, you have overpaid. You're still not using the optimal power level, and it's overall bad. So that's when we started to build a display wall that will be driven by virtual machine. And the topic today here is that one of the key aspects of such a construct is to have some kind of video coding mechanism which leaves the CPU unburdened with the tasks of encoding. Because I mean, I've seen, actually, my supervisor showed me a master's thesis from Italy, and I think it was published like this summer, where a couple of people set up kind of a similar thing, but I mean not as advanced, but they tried to just stream a video from a PC to a wall which was driven by 4 Raspberry Pis. It's kind of cool because you have low power consumption because of you use Raspberries. They used general tools like GStreamer, FMPEG to encode it, and well, the first conclusion to which they ran into, which I was aware of, that yeah, they waste all the CPU. They were able to encode the video on CPU and just send it over, but I mean, you can do nothing more on the CPU. So in my situation, where I need to run actually a virtual machine which would actually perform some tasks, that's totally not an option. So I was stuck for a while, but then I become aware that well, GPU vendors are starting to introduce general purpose H.264 encoding capabilities in their GPUs, and well, that was the point where where kind of all the pieces fell together, and I was like, okay, I have a virtualization mechanism, I have an encoding mechanism, so that's just a point where we can build up a wall. And that's what I'm working on now, and I'll tell you more about all of that. So, so what is NVEnc? NVEnc is hardware encoder which is integrated in the die of the Kepler Maxwell GPUs. It's in some way similar to what you mentioned, the Intel Iris HD. But Intel Iris HD also is a GPU component, but it's embedded in the CPU die. So that kind of suffers from scalability issues, because while you can stack multiple GPUs in a system, you can't scale multiple CPUs. I mean, it's especially bad for i7 because they only allow one CPU. If it would have been Xeon, you would actually at least get 2 or 3, but I don't know why they did that. And it provides means to perform real-time video encoding. So this is also another criteria for me, because there of course are cards which are specially meant for video processing, which provide encoding capabilities, but they're mostly targeted for, let's say, transcoding of media, where you have some kind of an TV station or broadcasting system, and you have some kind of, let's say, Full HD content, and you need to transcode it for the use of mobile viewers and desktop viewers. And there's, in that case, it's not so hard, it's not so important to have real-time performance, because, well, the user can wait and preload it. It's much more important to remain the quality. While for an actual OS to be streamed over to a wall, the latency of the encoding is the main aspect, because nobody's going to use a system that introduces a much larger latency than a real hardware-based display wall does. So, why NVEnc actually came out? At this point, the encoding technologies I already mentioned, Intel HD Iris and NVEnc, as funny as it may seem, but they're mostly being used in the common market as a way to stream games while you're playing. I mean, if you want to show somebody how you're just driving in GTA, you can just make a video card encode all the video signal in parallel while you're gaming, and stream it to an internet service, and give somebody a link, and they can watch you play. But at this point, I haven't seen Intel do anything really spectacular with their Intel Iris HD. But for NVEnc, NVIDIA actually has a grid virtual GPU thing, which is actually kind of cool, and which is in somewhat similar to what I'm doing, but still going in different directions. So the grid virtual GPU is a thing that allows multiple people to take use of the resources of one physical GPU. You actually mentioned a really good example of CAD modeling. Well, this is a perfect scenario, and this is one of the showcases I marketed. That if there's a company which has like 30 engineers working on designing a car, well, what are the options? Either you buy a cool PC for each of them, so they can each do their work, or you put in a grid card. The grid cards have the capability that they simulate multiple virtual GPU cores, and they use some kind of patched, I think it's Xen or KVM, I'm not sure, where they actually allow each virtual machine to use one of the virtual cores. So you can have like 4 people doing parallel CAD work, which all comes down to one physical GPU. Which is kind of cool, because you can utilize the power of the GPU to its full extent. Not like the person would be, let's say, using his desktop computer and only reaching like 50% of the maximal power you can get out of the card. Well, this is a really good way to provide desktop virtualization, but it's somehow, I don't know, maybe it's because of the business model, but this technology is available only in the high-end grid cards, so it's quite expensive. So if you don't have like actually 30 people working on CAD, it's not much use of buying it. And another issue is that why NVEnc? Because when they all work on the same card, they have to stream the data somehow, because there's not like an actual desktop where you render it. You're basically working from a thin client on a virtual machine. So that's why they also saw that, okay, let's take the industry standard of video encoding, let's take H.264, and let's just make a hardware chip, so we can directly access the video memory, compress it, and stream over to the thin client. That's a great concept. I really must agree. And here's image from NVIDIA's site. I think it allows actually to better understand what I just tried to explain. There's a virtual machine, the hypervisor, which is either Xen or KVM. And there are virtual GPUs, which are all basically going down to one physical GPU, which then takes the video data from the frame buffers, it compresses it, and it sends it to the desktop client. I've tried to investigate how flexible this is, and again, they have like a hard-coded limit of video outputs for each card because they don't actually need it. I mean, for a CAD engineer, it's enough to have 2 monitors and be able to do everything. They have, the main thing here is ability to scale among individual desktops. So it's kind of, I hope that in the future slides it will be become obvious how this is different from what I introduced, because I mean, at this point you might wonder, because I also mentioned virtual machines, display walls, lots of displays, virtualized graphics cards, so how is this different? So we have a virtualized display wall in University of Latvia, where we are conducting our researches. And we are using the virtual machine as an abstraction from the underlying physical video card. So if in the case of vGPU, it just provides a mapping, we run a virtual machine where the graphics editor is totally simulated. We can configure it as we want, give it as many outputs, dedicate as many memory, which actually resides in the system memory of the host, so you can access it very easily, and give the needed resolutions. And in this way, we kind of move away from the monitor to physical output bind, which is introduced by building a hardware system. And the host system runs the virtual machine, uses H.264 to encode the data and stream it to a display wall. The display wall itself is again run by monitors which are each backed up by Raspberry Pi. Why we chose Raspberry Pi? If honestly we would have taken any embedded system, which is which allows the needed codec, but Raspberry Pi was at that point one of the cheapest and one of the most easy to begin development. They had a really open API, and they supported the Open Max standard, which was really easy to use to write the software for the coding. I've currently looked into other boards. There's some alternatives like Banana Pi and such things. I mean, they're really impressive at the terms of speed because they kind of overstep the boundaries that Raspberry has, but they are lacking openness in terms of code. I mean, you can run pre-built applications, but if you need some extensions, it's really hard to do something because it's all closed. So here's a scheme to show how our project is working. So we have this physical machine, the server. Currently it's an i7-4770R CPU with an Intel Iris HD graphics. Inside that, the host is running Windows and it's using a virtualization system, and it runs a guest OS, which actually runs the content that is streamed to the virtual machine. And so we use the virtualized graphics adapter. We have our software stack that gathers all the frame buffers from the virtualized graphics editor's frame buffers and uses a physical card, in this case Intel Iris HD, for H.264 encoding, and then streams it over Ethernet, gigabit Ethernet to be exact, to the embedded systems at the back of each display. At this point, we're running 16 displays, each at full HD, and gigabit is more than enough for that, even at frame rates close to 25 frames per second. That seems really nice. And I mean, since Raspberry actually can handle more than 100 megabits, it's really good that we are generating such a low bandwidth, because if we had to overstep it, we'd have to obviously choose another embedded system. And here are some images of the actual wall. Here's an example of just seeing how that Windows actually works and allows you to scale everything. So this is a virtual machine, Windows, running inside the host OS. It thinks it has 16 monitors. You can see that, well, as for the first monitor actually does the start thing and everything. And I've driven Google Maps window all through that, so you can see how it looks. This is an example where we try to run CCTV surveillance software, because that could be one of the obvious applications for this, where they need actually really high resolution display walls to combine video feeds from multiple cameras in city. And this is the back of the wall. What you can see our networking infrastructure. We have a big switch. Each Raspberry is connected to the switch via an Ethernet cable. These holes are openings to the backs of the monitors where we have an HDMI input and the power cables for the Raspberries. We actually thought it could be cooler to drive them with power over Ethernet. That could be an improvement because now this wall actually is able to blow the 30 ampere fuse. So not very nice. Yeah, these are some milestones about what we have achieved now. So this setup, 4x4 at Full HD, it's actually running really stable on common applications like YouTube, browser, Office applications. I mean, you can do all that stuff without any issues. Latency is good enough. I mean, I myself don't feel any difference like working on a normal PC. We tried to run the CCTV simulation. Well, the results for 16 live camera feeds were good, but when we went up, we started actually seeing issues. And this is where I'm looking forward to using NVEnc, because at this point where I have the i7 with the Iris Pro, I can't go any higher because, as already explained, the Iris Pro is integrated in the CPU die, so I can't add any additional hardware components to actually increase the computing power. We have another server with 2 Xeon CPUs and the Tesla provided to us, and I hope that it will boost the limits, and because we have actually some people being interested in the CCTV setup and they want 64 cameras. So with this, it's not enough, but if we can boost it up, we could actually match these. And if that works, that's already a great improvement over the existing stuff. Because if you do some little calculations, so it's roughly 48 megapixels total, something like that. So I don't think it's, I mean, you can do that with a lot of PCI Express slots and a lot of very expensive video cards, but if you can do that with that system which is driven by one i7 and a GPU, I think that's a really good result. So, yeah, why NVEnc could be better. Intel QuickSync, and Intel QuickSync is a framework, how they call the stuff they have inside the Iris HD. It's a media API provided by Intel for the encoding and decoding. And Intel QuickSync and NVEnc are currently leading ones. As you already mentioned, yes, AMD also has something in their ATI video cards, but at least as far as I've seen, they're not so good. And also, your results about teraflops kind of correlate to that, if you look at it that way. Intel QuickSync has, at this point, proven to be the best. There's an annual conference that does comparison of H.264 codecs, and I'll show the graphs, which has actually stated that Intel QuickSync provides as good quality as X264, which is one of the most popular software libraries for doing this, while keeping the CPU at no use. So that's kind of cool. At that point, when the conference was held, NVIDIA basically offered only Cuda-based H.264, and I assume it could be not as effective because I think for video encoding, using dedicated DSP is much better than trying either to use FPGA or some kind of parallel computing, because if you have a straightforward signal processor, I think it's much more efficient than if you write a CUDA algorithm for that. But as I mentioned, Intel QuickSync suffers from the scaling because the implementations available are mostly in the CPU dies, so basically you get one card and you're stuck with that. So looking at what I mentioned, these are the graphs, and to explain the context, these are graphs where each of the encoders were run at the highest speed present, because that's at least what I'm interested in, bigger speed and small latency. So as we see here, the Intel QuickSync was, well, quite highly above all the others, and here we have. I think the main concept was a third-party company that did their algorithm on Cuda, but it's also basically well, I think if they have conquered the market, then it should be at least quite good. But this shows that, well, at that point, Intel QuickSync was way beyond, way above the other results, and that's why I chose it for the first product of the wall. You can see that if you look at the total frame rates, and this is for Full HD, the total frame rates is, for Intel QuickSync, it's about 500 frames. So it means if you divide it by 25, you get, well, around 21. You could actually encode around 20 monitors at Full HD at 25 FPS, which should be a good FPS for a person not to notice a lag. So this already was quite promising. Then Maxwell came out, and at least this is from NVIDIA marketing PDFs. Well, they are promising quite big numbers for Maxwell, and you can see his increase from Kepler at Full HD. And if this is as good as I promise, then scaling these cards in a system would actually quite remove all the boundaries. Because if you can like scale 4 or 5 such cards in a system, then you can get over 1000 FPS for Full HD, which is quite cool. And just to compare, not to be confused, because previously I showed that Intel was was getting 500 FPS. These are tests done on a previous generation of Intel cards, Intel CPUs, which had only about 200 PCs, 200 frames. And this is a kind of to demonstrate how Maxwell goes over the limits of the old Intel performance numbers. So if this is roughly what I'm getting with my Iris, because it's not the best card, and the CPU is also mobile, so it suffers from the power reductions. But this should demonstrate that the numbers at least promised by NVIDIA, and I hope to get my own numbers when I finish integration of the Tesla card, which could be a bit over the top, because I mean, maybe targeting Quadro cards, which are, I mean, cheaper but still have kind of the same functionality, would be wiser, because I think Tesla is still more targeted at people using the Cuda cores, not the encoding stuff. But well, that's the best we have. And when I have that, I hope to publish some numbers on how much FPS I can actually push out on the whole wall. So, yeah, at least from the public numbers, which are not generated by me, so it's just speculation, that the Maxwell speed could be equal or even better than the Intel QuickSync ones. So it would be a really good candidate because of scaling opportunities. And currently, yes, we are trying to integrate Tesla K40 and GeForce in the system we have, and try to compare them with Intel QuickSync. Well, the sad news about GeForce is that, I don't know why, I think it's again marketing, they have limited the ability that you can have only two encoding sessions in parallel. So that doesn't give you like more than 2 monitors, but I hope that the results with Tesla will be good, and if that's really good, I could try to get my hands on some, I think, Quadro cards and compare how that scales, because, well, Tesla is still, I think, out of the price range. If you have to set up a system with 5 high-end GPUs, or Tesla, kind of breaks even. If you compare it to an i7 with an Iris HD, yeah, that's cool. Well, if you compare it to the PC with 2 Quadro cards, that's also already an option, because, well, the low-end Quadro cards are not that cheap, not that expensive, and basically the system needs nothing more than the NVMe chip itself. It doesn't need like a great amount of RAM and such features. Yeah, so thanks. And do you have any questions?
Yeah. Do you have any questions?
Yeah, I want to ask, you said you use the Raspberry Pis just to get the feed and then it decodes it, shows it on screen. Have you tried like any feedback? Like right now you said you can do everything, you know, on a PC, you can scale the windows and you say you don't see any lag and so on. But that is when you sit at i7, you know, the box that actually transmits the feed. I know that is not the purpose of the project, but have you tried like having 16 computers, basically like grid, you know, where you have like 16 PCs, everybody like sits on the internet, watches 1080p movies, and at the same time everything happens on one PC.
Yeah,
So basically
we have
you
that
use
idea.
Raspberry Pi.
If you look at our roadmap,
Yeah.
as soon as we're done with NVIDIA integration, we have then one of the next tasks is basically to explore the interaction options because, yeah, as you mentioned, currently it's only one person. And as far as that we've seen, Microsoft provides a great SDK for actually, it's called multi-point SDK, which allows applications to actually take benefit from multiple mouses. And the next step we're going to do is make up some sample applications, and I hope to get some first-year students for that. I think one of the best examples would be either modeling or some flowchart layout.
Yeah.
And I'd actually try to compare if 4 people laying out a chart is actually faster than one person doing that at a single PC. And if it is faster, what's the factor and is actually efficient? Because apart from that the high resolution is really cool for visualization for the users that need that, it could also be very productive for interaction. Because I mean, if you have a really like an OVL graph or some kind of UML model, which hardware's things are the best because, well, I mean, you have to generate the image of that resolution to actually output somewhere. I mean, since console gives you full HD, the best thing you can do, if you just upscale it, it will be, well, corrupted. So you need some kind of, to make the game think it actually has the virtual display as big as you have it. So that's, yeah, another...
There's lots of software limitations. You can't do anything in console, basically. Some years ago in PlayStation 3 you could run Linux for a brief time before Sony shut it down, and there maybe you could basically hack it to make it high resolution.
Yeah.
Because it shouldn't be that hard technically,
of course,
but you can't really do anything. So.
No, but
PC games, yeah.
Yeah, I mean, if this really works for PC games, I think that that's at least I myself will be very glad. I mean, I will build myself. Actually, when if I talk about the experience, we built this wall. It's 4 times 400. Each is 22 inches. Well, I mean, what I'm feeling is when I'm standing in like 4 or 5 meters from the wall, if you use Windows at its native scale, things are actually too small. I mean, you have to zoom in everything. It's we're now running Windows with the display set to. We have the ability to set to 150% of like magnification. Then it's okay. At normal scale, you basically it's too much detail. So at least for me, it feels like if you would set up, well, let's say 3 times 3 displays of such size, it would be totally efficient. I mean, it would actually cover the same surface. You have lower resolution, but I mean, there seems to be a point where at least one person can't actually use all the pixels. If it's more persons, you each working at a segment of the wall, then yeah, it's nice. But I mean, for one person, and especially for gaming, if you have like a 3x3 monitor setup, I think it's quite nice.
You also need borderless like monitors.
Yeah, we've looked at that, and this thing is, actually, we could take these apart. I mean, I've really seen a lot of people that say that a couple of Samsungs, if you remove the borders, they actually don't have very big hardware. Yeah, there are some which have actually big metal boundaries here, even under the lid. But there are some monitors which have really small ones. But there are LG manufacturers, some like common access displays which don't cost like 2K with small borders. And one interesting thing I saw while preparing for a poster is that a company in US actually making a glass overlay, where you take off the border and you put on a glass overlay which has rounded edges, which kind of emit the light, so that you don't feel the thing here. It takes the pixel from here and makes a curved edge. So it actually, I mean, it's a bit blurry, but you basically don't feel that there is a break. You just feel that some parts of the picture are a bit blurrier. But that's an interesting approach, of course.
It's like ambient light, something like that. I think that Philips, LG, and some other companies now having it. Basically, it's in a mid slide to the back, but still you can have it. You could also try like 16 projectors or something.
Well, the issue with projectors is that you're kind of limited the layout space. I mean, because with the wall you can put it anywhere you want. With projectors, you need the viewing distance, and I've actually seen a lot of papers where people try to do that with projectors, and the issue with projectors is color calibration. It's harder. I mean, if you have similar displays, you can, well, try to at least, because our world doesn't do any adjustments. Well, it's bad, but it's not an issue at this point. We have similar monitors, we have similar settings, so it works. If you have projectors, even the surface where you project on can cause issues, and there's a lot of people trying to battle this single issue, how to calibrate a setup of multiple projectors to actually have the same color field. So it's nice because, well, projectors are in some way more attractive, but it's not that much hardware. It's kind of, you can't just bump it with an elbow or something. But again, the deployment issues and calibration, well.
No borders though.
No borders, yeah. But somebody just jumps in the air and you have his head somewhere in the middle of your wall.
Projection.
Well, yeah, that's another vision. Then you must have a cubicle. Yeah. Well, I mean, it's all about deployment.
Okay, by the way, this is a draft of the poster we submitted to the media for the next GTC conference.
I think this is the actual poster, no?
Yeah.
Yeah.
It's draft because it's not still approved, because approval will be lately in autumn. I hope we did it through, and I hope we created some very nice design for that, because last year's, you see how different.
Some were really bad.
Yeah, last year's participants, and they are, I consider like the design nightmare or something like that. They're not quite pretty. So I hope we created something a little bit more aesthetical and a little bit more some structured thing. Let's see how it goes, but I hope we will appear there at the next year. So yeah, please, last speaker for today. This is cable for that.
Nie wiem, czy to flash jest. Nie, jest no tak. Doktor tutaj ma kierunek studies. Nie wiem,
Okay, so I'm Harijs Grimbergs. I'm from Riga Technical University, Autonomous Systems Laboratory. We just call it the Robotics Laboratory. And I will tell a little bit about object tracking in 3D space, mostly in 3D point clouds. But I understood when I was making the presentation that I should probably give a little insight on what is a point cloud and more about image processing and so on. So I basically divided the presentation in 3 parts. The first is like a little intro in computer vision and point clouds. Not like a detailed intro, but more like I talk more about parallelization in general. Like it isn't tied to Cuda. Cuda is just something I'm more interested in. It is something that is tied to my doctor's thesis, and that is also something you can actually learn in the Riga Technical University, and that is where we are going. And the third one will be what is done exactly, like experiments and like a video shows like several things that I have done in my master's thesis and so on. And well, what is done is also, of course, some other people's work, like for example, this Google self-driving car, or recently, like a week ago, Audi took a car autonomous on a high-speed circuit in Germany, where it drove like 220 kilometers an hour. And all of those use point clouds, and I will explain why and give some more information. So first of all, like from computer vision perspective, when we're talking about computer vision, most people see images, 2D images, like let's do calculations on them. Well, the problem is well, they are very useful for things like identification, like we can find cars, we can find people, we can track faces, like we have demonstration there. We can basically do lots of things about classification, identification and so on, but but the image itself, of course, is two-dimensional. Like here I rotated it slightly so you can see it is a plane. So, and everything is in pixels. That means without knowing anything about the scene, and even if you do know something about the scene, you still can't get real, like physical data from an image. Like you cannot get the size, for example, of the bus, because it is like, for example, 83 pixels, and if it goes further away, it gets smaller and it's less pixels. And you can't actually convert pixels into meters, even if you, for example, if you know the size of the vehicle, even then you can technically do it, but still, basically what you fall into trouble is with optical illusions. Like if you have a large car very far away, small car very close, and with one camera especially, you cannot actually know any difference. So that is why data like this, one-dimensional, even like structure from motion, when you move with the camera, you get like a 3D model of a vehicle or an object. Even in those cases, the data is actually like in the wrong scale. Like you cannot measure the distances between those because you just like data. And the thing I research most and I have worked most with is 3D point clouds. 3D point clouds is basically, we can see here, it is the same image. We still have the vehicle at the bottom, but you can see here that the plane itself is basically, the pixels are pushed in it's like third dimension in 3D space. And the 3D pixel we call a point group points we call a cloud, and this is a 3D point cloud. And the advantage in this is not because you have third dimension actually, but the advantage is that the coordinates of each point in the 3D space is in real world units, in meters, for example. So now if I want to see like the width of the car, then it is 1.8 meters. If it goes further away, it is still 1.8 meters and with certain accuracy and certain noise. And if I track that vehicle, then I know speed in meters per second. So basically this data is a lot easier to use. Like for example in a computer, in a safety system, which I will show later, for example, you can actually see the distance to a vehicle, and then you can basically do a check to see if you are too close to the vehicle, if the braking distance is too large and the vehicle is too close, so for example brake, something like that. And this also allows things like the 3D representation means that you can also basically find objects not because the way they look, but because the physical properties, like the volume they take up. So this allows things like detecting not only vehicles but people, trees, pigs running over the road, something like that. Everything can be detected. That is why it is extremely robust, and that is why it is constantly used in robotics, in autonomous cars, and so on and so forth, because you can basically make 100% safe system, because it will see what is visible. What is not transparent, you will be able to see, and it will work, and you can make...
It might sometimes happen here, but but it should be all right. At least 10, 13 minutes more, because I was said downstairs that there's a security training tonight, so they might start.
We will have to evacuate.
Yeah, we will have to wrap up. 9:30 approximately, so it makes sense.
Okay. So there are many ways to get this data. One is stereo cameras, basically the way human eyes see. You have two cameras, you can triangulate the distance to every pixel that both cameras see. It is very good because it doesn't emit any energy, it is very energy efficient.
Uzmanību, godājumie darbinieki un apmeklētāji, viltus trauksme. Lūdzu, saglabājiet mieru un atgriežieties darba vietās. Внимание, уважаемые работники и посетители! Ложная тревога. Просим сохранить спокойствие и вернуться на рабочее место.
So everything is fine.
Okay.
It's just to make sure that everybody's awake.
So and it can see far away, because it basically depends only on the distance between the cameras. The larger the baseline, the further you can see. The second one is, for example, time of flight camera. It emits infrared radiation or infrared light in like a sinusoidal pattern. It reflects, it sees like how far the light has flown, and you can calculate this distance to objects. And the third one is, for example, LiDAR, which is laser-based, which is most popular in most vehicles, autonomous, especially the Google, for example, self-driving car. But it is extremely expensive usually, and it takes also a lot of energy to operate, which can be very prohibitive in small robotic applications. So when we're talking about parallelization, parallel processing, I just said Cuda here, but it is also OpenCL, OpenMP, like anything can work. Computer vision by itself is embarrassingly parallel. That is, like, I think, the correct term, which is basically means every pixel in many cases can be separately, the calculations can be done on them separately. So on Cuda, for example, that would mean there's one thread per pixel. You can create as much as threads as there are pixels, and you can do everything in 100% parallel way. But well, there is slight problems. For example, in very basic algorithms like thresholding, where you just look at the color, you see it's larger than something, you take one result. If it's smaller than something, then you take another. In that case, it is extremely fast. Those are the fastest things you can do with parallel computing and visual algorithms. For example, here we just need to look at the pixel in the middle, for example, the green pixel, and check if it's larger or smaller than certain value, do something. There are a lot bigger problem is when the data is not local to the pixel you're actually computing. For example, a blur filter, where you just want to average the neighboring pixels, like here, you have to access the red pixels that is around the green one. The problem here is that GPUs work basically in cache the same way as CPU. When you take a pixel, it will load like in batches. It doesn't load like one pixel. If you make a kernel, you make it load data, it will load, for example, 64 kilobytes or something like that, and when it loads it, it is very fast in that loaded cache, but if you look something outside of that, then it also gets slow again. So for example here, if you for example look at pixel 30, then it will also load 31, so accessing that will be fast. But for example, in the next row, the numbers basically show how it is laid out in memory. So I have 9, 10, 11, then there's more pixels, then there's the second row with more pixels. And so if I look at pixel 50, it could be like kilobytes away, so much more than the cache size. So accessing that pixel will be a lot slower than accessing that. And it will not be a lot slower, of course, like GPUs are meant for that. And there are ways you can optimize it. Like Cuda supports textures, textures have more caching capabilities, and there are ways you can go around like this speed problem. But why I'm saying that is because in 3D point clouds it is different. We have a larger problem. In Pixel you usually do like searches in or calculations in a neighborhood, a small, for example, place. Like if you want to calculate something on the pixel 30, you just look at 29, 31, and you can do calculations needed, like calculate a gradient or something. In 3D point cloud, that means those pixels might not be the closest together. For example, if I want to see the neighboring point, this is for example in a 2D image, a stereo image, we will get like an image like that, a projection. And if I want to see like the closest pixel to 31, in a regular pixel image that would be 30. In a point cloud, on the other hand, if you look from top down, then the closest point to the blue one is the red one. So that is actually closer to blue than the green one. Basically, the third dimension, the third, like the positions make it a lot harder, and it makes the addressing and the referencing of data a lot harder. So here it is 01, so basically it is constant time. You know, you take that minus 1 and you get a point there. On the other hand, if you are here and you want to get the closest, you basically have to search the whole point cloud, or if you haven't done any pre-processing on it. And that is problems why even on GPUs and why parallelization of point cloud, some of the algorithms is very hard, because you basically have to search the whole data that is on the GPU at that time, and that is not that fast. And but the bright side is that the physical, like if you get a point cloud image, you will see that, for example, from stereo camera, it looks like a cone. It is like the field of vision, and then it goes out, and the point and the pixel in the image is like in a straight line. It is a vector that is straight from the camera to the world. It is not in any way bent. You know, when you do any kind of transformations, they are like linear in that way. That will never, the data will never be like that. So you can still reference in a 2D grid. So even if you have a 3D point cloud, you can really do look like a 31, then you look at the 30, you reference. So basically you have a pointer array, something like that. You check that point, you measure that distance, it is larger than, for example, certain threshold, like 2 meters or something. Then you look at the next one, and then you basically look around the pixel, like in a regular 2D like image processing, and you get actually points that are technically could be the closest, because at some point it basically moves like off. For example, like the red point will never be on the right of the green one. So there is no distance, no camera calibration, no optics, no way in any way that the red one will be somehow to the left. If it is in the image, it is to the right. It will always be to the right. And so you can still use 2D references to greatly increase the points basically searching in 3D space. And that is, for example, I use that in segmentation, where I can actually segment objects that are far away, and I can do that without very slow like iterating over the data. And when I will give like a brief introduction in the algorithms themselves, I will not go into detail, but basically I worked on a project. It was for a GCDC, that is Grand Cooperative Driving Challenge. Basically an institute in Latvia was participating in it. They made a car. Those cars are not autonomous, but those cars need to talk to each other, and they need to like drive in certain speeds that in rows and so on. So they need to be like cooperative. It is not like having a camera seeing that a car brakes. It is that the car in front actually tells you that it is going to brake. Like it tells you that in 1 second it is going to brake, and the second car can react before actually happens anything in real life. And but they still needed like the security features. If something went wrong or something like that, they still used the sensors. And the idea was that we could use stereo vision to track, to have this, to get point clouds and to get detect objects in point clouds and track objects in point clouds, and do that everything in real time. So because we have to do it in real time, because that is like a security feature. I can't do it in offline mode when there's already an accident, and I can't do it like 1 frame per second. I actually need you can calculate actually how much frames per second you need for that. So the first step in that software was, for example, ground detection and removal. That is also required for segmentation, because basically ground creates a gradient in like a lot of points. Like most of the points in the point cloud is basically ground, and you have to get rid of them just for speed reasons, and so there wouldn't be any like ground. You detect ground as a distinct object, and you start slowing down for no reason, and so on. There was also, it had to be done in real time and very fast. And if there is up to like hundreds of thousands of points in one frame, in one point cloud frame, to get it real time, actually reduce the dimensions of the whole thing. And I just looked at the XYZ space, YZ space. That is Z is that direction and Y is vertical direction. So I take all the points, and then I try to do RANSAC, that is random sampling and consensus algorithm, that basically iteratively tries to find the best fit for a line. And as I said, most of the points are on the ground plane. So the line that will be found is on the ground planes, and that is pretty fast. But that is also something GPU can benefit from, because that iterative algorithms like that. So I get angle, I get height from the ground. I get that is, for example, 1.5 meters from the ground. Then I remove those regions which are not needed, and we can see here. I also remove the top, because sometimes the algorithms that calculate point clouds from the stereo vision, they calculate nonsense values for sky. So they think like a cloud is 2 meters from your face or something like that. And so basically I remove everything that is above a certain height. And and that is also to get rid of bridges, arches, things like that, so they don't interfere with anything. After that, then I have to detect the object themselves. As I said, in point clouds you don't have to look at colors or special patterns. You don't have to actually teach the machine how, for example, a human looks, because at that point it doesn't matter if it's a human, if it's a tree or a car. You just don't want to crash. That is the only thing you don't have to do. There is zero reasons what the object in front of you is. Maybe like in the worst case in future there could be an artificial intelligence that basically plans the least of the worst case scenario. Like if you have to hit a tree or hit a person, it will choose maybe, I don't know what to choose at that point, but still it would choose the least bad thing. Right now the basic idea is that you detect everything and you try to like not hit anything. And that can also be, for example, here I tried one of the things was plan view occupancy maps, that is from the top down. So here is the camera, and from the top down I see I make basically in grids, for example 10, I don't know, meter times meter or 50 centimeters times 50 centimeters, like grids, squares, and then I see how many points are in those squares. So walls actually make basically the value in that bin that was called here is much larger. Then I filter it out to get any away from noise, and then I actually detect objects. For example, in this case there is the car, blue car here, green car here, and here is the bins. For example, you can see that there are a lot more points here and a lot more points here. The filtering is done by Gaussian filter, so you can actually see the Gaussian distribution. And the maximums basically represent the object. So I see, oh, there's two maximums and there's two cars. There's actually a third car in front, which is also detected, which is the yellow line underneath. You don't actually see any head here. But you can see that actually detect objects that are partially occluded that I can't actually usually detect with a regular image analysis. Because usually cars, for example, are detected using symmetry, using shadow on the ground, and so on. There are many algorithms to do it from one image. In this case, though, the most algorithms would fail. But in 3D point cloud, you still see it because it's a physical object, like a physical thing in the world. Then there's the segmentation and tracking itself. There was basically the segment, everything had to run real time on a CPU at that point. We didn't actually use GPU. So in the CPU implementation, it is like the algorithms you have to use and the make is, they have to be as computationally least expensive. But still, the segmentation I used in volumetric segmentation, because as I said, everything is in meters, so I can constrain, I can do thresholding, I can do everything that normally could be done in abstract values that you have to tune. Here I can just say, okay, detect cars that are larger than, I don't know, 3 meters, and it will detect everything larger than 3 meters or something like that, or smaller. And then I have to take into consideration the noise, because in stereo vision the error in calculations is actually exponential, and it is exponential pretty fast. For example, in my case I could track a car to 45 meters, but at 45 meters the error in the point calculation is actually about 6 meters. So if I wanted to track a car at that distance, I couldn't say segment everything in 2 meter Z region, because the error itself is more than 10 meters at that point. So the car is actually 10 meters long at that distance. So I had to take that into account if I wanted to track at those distances. And the last thing that was in that software that was developed and the algorithms that were made was ego motion compensation. Ego is the car itself, where the cameras are, the system, and it was necessary for calculating who actually moves, because the point clouds are calculated relative to the camera. So if I drive at 100 kilometers per second, a car in front drives at the same speed, I will actually calculate the speed of 0, because it doesn't move. Everything around it moves, but it doesn't move in the relative space, So here I use stereo vision based visual odometry, because if I have two cameras, I can actually use the same point cloud, to track points in it, and I can calculate my movements also in real life, like units in meters and so on. So I could actually calculate my own movements, then I filtered it, then I got over time speed, and then I basically compensated the trackers so I could actually see that the car is moving, and or that I'm crashing into someone, or is someone crashing into me, or something like that. And so there's a video I will show. Basically, first of all, this is how the point cloud looks like. This is from the so behind you. It looks like the image almost. And if I move in it, for example, I move slightly upwards, you can see how how noisy it is. So, for example, here you can see the car. There is actually a car, and the car is like smushed out in the Z direction. Lasers, lidars and laser-based systems usually don't have this problem. They have like up to 100 and more meter like detection, and the point cloud is with pretty good accuracy up to even those 100 to 200 meters. And they don't have like this exponential error that stereo vision cameras have. But I still manage to detect objects in it. So this is, for example, the traffic sequence. So here the bounding boxes are three-dimensional because everything is 3D in that, so I can actually take the volume of the car, and the speed, the distance is in the middle, so that is 24 meters and that is 17 meters from the vehicle itself, and the top is speed, so I know it is moving like at certain meters per second, and I know what my speed. The ego speed means that I'm, for example, moving 6 meters per second. At the right side is the map, because I can, as I said, I calculate my own movements. I can actually draw a map where I'm moving and create some interesting stuff with that. So those are the trackers, the points, and you can see that I'm basically detecting objects. When the object gets occluded, I of course don't see it, I stop tracking it. Then when I actually see it again, I start tracking again. I don't actually look if that is the same object. For now, I didn't use any classification. I didn't check if that is a car or a bicycle rider or a pedestrian. I don't actually check anything in those cases. This is, for example, around the corner. You can see that I tracked the vehicle itself, like around the corner here, and it kept tracking with a certain error. And as I said, I can track anything. So, for example, this is me like walking around in circles, like up to 15 meters in this case. I tracked myself because everything can be tracked that actually can be segmented. Then, as I had the map, I actually can take those point clouds and put one after another, basically, or recreate like a three-dimensional like object. This is the same, for example, tracking sequence from top down. There's the street. There was actually the 3D one with the turning is better, but I don't think I added that. Basically, I can recreate the street. That is a different use. That is also very popular. And actually, I know that there is a company in Riga right now that is 3D scanning Riga. So they are using lasers for that, because that is a lot more accurate, and that is the point. But you can also use something a lot cheaper like that. And the second thing that was tried was, so the first one was car, basically security system, adaptive cruise control, progressive driver assistance systems, things like that, where I could actually inform that crash is about to happen, something or something. The second was robot control, because I work actually in the robotics laboratory. So here, for example, there's a robot just tracking hand. That is the same algorithm that tracked the car. That is the same algorithm that tracked the pedestrian. Here it tracks, for example, a hand, because again,
by taking frames with